to mind when talking about sand reclamation. The common answers we normally get, the positive answers are recycling and reusing. We're trying to reuse that sand as much as possible. It has an environmental benefit, which leads to sustainability. And we're trying to remove binder from the sand and control our elements. Now, the negative comments to that is it can be a complicated and expensive process. It's only for large foundries. Not sure if it's worth the investment. Doesn't work with all binders. And that famous foundry saying that we've all heard is, we've always done it this way, so why change? But the first things that I think about when we talk about sand reclamation is we're trying to lower our operating costs over a period of time. It's not immediate, it's over a good period of time. We're trying to close that loop for foundries to make that a circular economy or be part of that circular economy. We're looking for more consistent casting quality and also to comply with environmental standards. We're future-proofing, and ultimately we're trying to reduce disposal costs. And obviously Simon sent out an email through the CMF recently on landfill tax, where I think there's 3 foundries in total. 2 foundries is going to cost them £2 million in terms of getting rid of their sand, disposing of their sand, and I think one was £500,000 per year. But we're trying to save costs on buying new sand ultimately. Obviously there's a need for optimising our sand reclamation system, so it's a new focus on foundry efficiencies. Obviously we spoke about part of that this morning with the energy side of it, but sand reclamation is a huge part of this. Again, with, silica sand is increasing in its costs, the disposal is increasing, and these trends are seen widely not just in the UK but across Europe. Other factors obviously is environmental concerns, CO2 emissions and increased haulage costs, and these all have to be accounted for. So just some figures. So these figures are actually taken from a European Commission called the Life Eco Sandfill project. And it's estimated that in Europe, unfortunately I couldn't find any UK data, which we've struggled with, but across Europe there's 9 million tonnes of waste sand per year. That's quite a large figure. Worldwide it's estimated to be around 100 million tonnes. Now we say that less than 25% of this foundry sand in Europe is recycled in other applications. I think that's probably best case scenario, to be honest, in industries like cement, tarmac, and obviously it'll be interesting to see what Ian speaks about a little bit later in terms of foundry waste sand and what the update is with that. But the remaining 75% of that 9 million tonnes in Europe is landfilled. Obviously with that there's a pollution element to it. So with global warming, potential of sand extraction, so we're quarrying alone and dredging of the sand, it's estimated to be between 92 and 120 grams of CO2 emissions per 1 kilo of dry silica sand. That adds up to, if we look at the 9 million tonnes per year, quite a hefty, don't know what's going on there, quite a hefty big number for CO2 emissions annually. So 1,080,000 tonnes of CO2 emissions. There's obviously also air and noise pollution associated with that. And also sand extraction itself is quite a large land take and considerable loss of soil. So it's estimated to be between about 0.4 hectares of sand lost per tonne of sand extracted. But once we've extracted that sand, it's not in a usable state. So it has to go through a process. We're trying to dry the sand and also classify the sand for foundry use. So for every 1,000 kilograms, 1 tonne of sand, it takes approximately 25 kilowatt hours of energy to dry that sand. And that's per tonne of sand that we use. So to dry 9 million tonnes, I want to get this figure across a little bit in terms of the numbers, because it is a big number and it's quite a shocking number, but 9 million tonnes to dry that is 226 million kilowatt hours per year. Now the reuse of foundry sand, so recycling and reclaiming that sand, would obviously dramatically reduce CO2 emissions and the energy used in that process. But what can we do? So as an industry, we look at sand disposal. It's just an inconvenient necessity really. So we're getting rid of our sand. It's a running cost. But what we need to do is have a look at the options we have, not only to save a little bit of money, but to become a little bit more environmentally friendly overall. Again, it's quite hard to condense this into sort of 20 minutes, so there's lots of information that's missing. But the first stage of this is primary reclamation. We're trying to break the sand back down to grain size. We're screening the sand to remove any oversized particles and metallics in the sand. And we're also creating a natural scrubbing and attrition just in the primary stage. And this primary attrition only, chances are that you're still disposing of quite a lot of sand. So good primary reclamation is always a foundation for good reclamation rates to begin with. But the principal controlling elements or mechanism for reclamation would be to introduce new sand into your system. So you introduce new sand to balance out your LOIs, so it's a usable reclaimed sand to use. So typically, if you look at an alkaline phenolic foundry, for example, 70% of that reclaimed sand is from primary reclamation, but we still have to add 30% new sand to balance out, to bring this sand into a usable state. But with that, we need to balance out our sand system. So if you introduce 30 tonnes of sand into your sand system, you have to get rid of 30 tonnes. You've only got so much space in your hoppers, in your silos. So if there were no losses or dilution from that new sand, the LOIs would continue to rise after every pass of sand until it becomes an unusable reclaimed sand. But what we're trying to do is limit the amount of new sand we introduce into the system. And to be able to do this, we need to introduce further reclamation or secondary reclamation systems. So just a few pictures of what we have available. So we have a USR on the top left-hand side, thermal reclamation, which is a well-known way of reclaiming sand, and also chromite reclamation. Chromite is obviously an expensive material, so we want to try and reclaim that as much as possible also. But the secondary sand reclamation refers to the additional treatment of sand after the primary reclamation stage. It aims to further clean and refine and restore the sand condition close to that of new sand, so we can then reuse it as a new sand addition almost, and especially for chemically bonded sands in particular. But secondary reclamation consists of thermal or advanced mechanical processes such as the USR. It removes adhered binders from the sand, reduces the loss in ignition, and ultimately it does improve the sand quality because we're reusing that sand that's already gone through thermal processes. The two types of main reclamation for silica sand we have is thermal reclamation. Obviously it's a well-known way to reclaim sand, and it works by reclaiming the waste sand stream to be reused as new sand. So for example, if we go back to the example I said earlier, if we're adding 30 tonnes in, we have to take 30 tonnes out. That 30 tonnes is what we use, typically a waste product, to go into the thermal reclamation. We can then introduce that 30 tonnes back into the system to be used as effectively new sand. But there is advantages and disadvantages to thermal reclamation. So advantages are 100% reclamation on all organic systems. We're using that waste sand to replace the new sand consumption. The thermally reclaimed sand is near zero LOI. It's not zero, but it's close to. And the sand is more thermally stable, so it reduces expansion defects in the casting. With our thermal in particular, we're trying to make it as efficient as possible. So emissions is one of the key points. So we're meeting all European VOC emission legislations. And 100% thermally reclaimed sand can also be used for cores, 100%. The disadvantages to thermal reclamation is it typically has a higher initial capital cost compared to other reclamation systems. Obviously there's a fossil fuel consumption, which is gas. We're adding gas, and obviously there's electrical consumption in there as well. And it's only can be used for organic binders. It can't be used for inorganic binders. We can't burn off any inorganic elements. If it's alkaline phenolic, we also have to add a alkaline phenolic additive, an anti-fusion additive into the thermal, and they require regular emission checks. But there is another option, and this is a USR, so it's a mechanical scrubbing system. And this system removes the need for any direct fossil fuel, so removing that gas straight away, and we're using a fully electrical system. It can be used on organic and inorganic binders, so it's not limited to one in particular. There's a lower capital investment cost compared to thermal reclamation, and also a smaller footprint. So especially in the UK, travelling around the UK, visiting lots of foundries, UK foundries typically have a severe lack of space to add anything like this into the foundry, but it has a smaller footprint than a thermal. But how it works, this is a brief introduction to it really. But the sand drops into a drum. I don't know if it's got a laser, has it? Yeah, here we go. So the drum here, this is the only part that spins. Inside this drum we have ceramic tiles, and these wheels are free rolling, but these are also made of a hard wearing ceramic. The sand drops in, and as this drum spins, the sand is sent to the outside of the drum using centrifugal force. And then we're just applying a controlled pressure between the rollers and the drum. So you'll see here on the left hand side, and we call it the sand scrubbing zone. So that's the area where we're really putting the sand under a little bit of pressure to basically scrub itself clean. But the advantage of this is it's a very, very controlled pressure. We're not using uncontrolled processes or impact systems where there's no real control to that. So for example, we can put as much pressure as we want depending on the sand type or the customer's sand type. And we can also change these rims here. And these rims basically hold the sand in for a little bit less time or a little bit longer. So the retention time of sand within the drum itself. But also it improves sand properties by rounding and conditioning the sand grain. So I like to kind of refer to this as almost like pebbles in a river or down the river, rocks down the river. So if you pick up a pebble from the river, it's nice and smooth. It's hit lots of rocks along the way and it's smoothed off all those sharp edges. And it does exactly the same with sand. And what that does, it improves permeability and the flowability of the sand. It leads to higher strength moulds or cores. And ultimately, because we're reducing that, we're rounding off the sand grains, we're reducing that surface area of the sand grain itself, we can reduce chemical consumption because we don't have to have as much chemical to actually cover the grain. But there's an example of, this is again, it's alkaline phenolic, but you can see it's a good example using alkaline phenolic because you get a purpley tinge to the sand. You can see this is before USR reclamation, and this is afterwards. So it's got almost like a polishing effect. And there's still elements of chemical within some of the gaps in the sand, but you can see that's a huge improvement. And in terms of the sand grain, it's nice and rounded. So you've still got some sharp edges here, but all these grains are pretty much nicely rounded. But using these systems, we've got a combination of the two, which what we try and do is figure out which one is best for the customer to use in terms of what their end goal is, what castings they make, and what chemical resin binder they use. But within combination, we can reclaim all types of sand and chemical processes. But typically, this is what makes it viable, commercially viable for foundries. Does it have a payback? So when we're looking at this is an example from a foundry using just over 5,000 tonnes a year of sand. And using a USR, with one pass through the USR, we have an estimated sand loss of 10%. That's through dust or sand stuck on the casting or just general losses within the system itself. Their new price per tonne was 40, it's in euros, but this is pounds, for £40, and their sand disposal cost was actually pretty cheap in this example. It's probably a lot more expensive than this. We've calculated all the electrical energy pricing and compressed air cost within it as well. And the investment cost, I mean, this is a very good example. This is a very good example, but the total annual cost without the USR, they're paying just over £200,000 a year on new sand coming in and the disposal of that sand. In this example, we have a 9-month payback. They're not always this good, but what we try and do is aim for that 2-year period. 2 years is the kind of sweet spot. But on top of that, what we're trying to do is also, this is what I really wanted to kind of show today, was the environmental savings to that. So if we take into account those figures I talked about earlier, with sand extraction, obviously the process and washing and drying, but not only that, the haulage to and from the quarry, and obviously the disposal to and from the landfill sites. This is based on just over the 5,000 tonnes per year of sand use. But in CO2 emissions alone, if we're reclaiming that sand, we're saving 172 tonnes of CO2 emissions, 766,000 kilowatt hours of energy used, and also saving 563 acres of land lost from quarrying. And this is just one foundry. So if we combine foundries together in terms of total savings of energy costs and CO2 emissions and land saved, it becomes, becomes a, what would you say, a very attractive approach to saving some sand and energy. But not only that, we're saving, there's some other savings here as well. So just, fuel, petrol, diesel, and new sand costs. This is purely new sand cost savings based on that 5,215 tonnes per year. But what we've done is not only, we're not looking at this as a capital expenditure. And what we've tried to do is take some of the points on board from foundries and what their pain points are. And especially for smaller foundries or people or foundries that aren't in a position to potentially buy this equipment outright straight off the bat. We've listened to those pain points I mentioned earlier on one of the first slides. It's only for large foundries. You're not sure if it's worth the investment. It's a complicated and expensive process. So what we're trying to do now in the UK especially is offer almost like a rent-to-buy scheme. So we're spreading that cost over that 2-year period, which is our typical payback time, to offer the best solution for UK foundries. And what this means is there's no capital expenditure to begin with, so we don't have to go through CapEx. It's a more cost-effective, manageable system. The foundries are able to then make a difference to not only saving costs, but also for the environment as well. And long term, after that sort of 2-year period where you've gone through the rental scheme, you then own the equipment. So after that 2-year period, you own the equipment. There's no monthly payback. There's no monthly fees. That is pure payback for sand. But a typical payback, so as a complete turnkey installed package, that includes all the overall cost of dust extraction, water cooling towers, the equipment itself, installation, using average new sand costs, average disposal costs, based over that period of 2 years, like we said earlier. And we estimate you can make a saving every month just on sand purchase alone. So just some really, really brief sort of calculations. It's probably around 2 to 3K a year based on average figures. Not a year, sorry, a month for sand. Now after that 2-year period, obviously that's going to increase. But if we link this now back to the original figures that we spoke about earlier, that 9 million tonnes of waste sand per year, if we take 25%, again, best case scenario, I don't believe it is 25%, but best case scenario, let's take that out of the equation. That's taking out 2,250,000 tonnes of waste sand to be used in other industries. That leaves us with 6,750,000 tonnes of waste sand per year in Europe. What if we can reclaim using the systems that I've mentioned earlier? Just an average of 80%. So if we look at green sand foundries, we might be able to get up to 70%. Alkaline phenolic, we might be able to do 90-10. But as an average, let's look at 80%. That means instead of 9 million tonnes a year, we're now putting to landfill. It's still a large number, but we're only now putting to landfill 1,350,000 tonnes per year. That's an 85% reduction. This also means a reduction in that CO2 emissions from 1,080,000 tonnes down to 162,000 tonnes. That's a huge drop. And the reduction of kilowatt hours as well, down to 116 million. That's an 85% decrease in CO2 emissions and 52% reduction in kilowatt hours. With that figure there, I have taken out all the running costs of a USR in this calculation as well. But yeah, very, very brief overview. Obviously, I've tried to get this in as quick as I can. But obviously, any questions, obviously, please ask away.